So now we are going to look at the calculate local gradients. We have already looked at the forward propagation. So I just start again here. That was example 5. Refresh. Okay, and I just go through the first step here. Now we're going to look at the calculate local gradients, which is the most difficult part. What does it mean? Well, let's focus on this note here. We have to calculate this one, the local gradients. So when I think about this, I think that the local gradients is what is the influence that this node has on the entire output. Okay, and what is the influence that this node has on the entire output? And you shall imagine that this could be several levels and several nodes in every level. So it's pretty difficult to find what is the influence of this node on all this output. Okay? And we have to use this because we have to change the weights here. The weights are wrong. But how much shall we change the weights? Well, we have to know the influences of the nodes. Okay, so if we run this here, this is the, and now I shall try to calculate the local gradients. Like this. So, okay, and we can see how do we do that. So this is the formulas. So we are using sigmoid at this point. Okay, so this is the node, so 0, 1, 2, 3, node neuron 3, this one. Okay, so the first thing we are doing is to figure out the mark. So what does that mean? We know that the output is 0.5 from this input, but now we need to know the rate of change. I think that's how they call it. Well, I think about it, it is the slope of this function. And if you take 0.3 differentiated, I think it's called, it gives us 0.24. Well, what does that mean? Well, I have drawn the green graph in, which is the differentiation. I think it's called differentiation. So we can see if we get 0 in, it's the highest point that you can get. So this means when I look at this sigma function, it's the steepest at this point. It should be somewhere around 0.25. Is it that? Is that the case? Well, you should remember this is 5 to 1. So if you imagine that this is 1, so 1 is somewhere around here. Okay, so this from this point to somewhere around there is pretty, it gives us, well, 0.25, doesn't it? If you imagine this point here and this point, you can see the area is somewhere around 0.2. If you go up around 5 here, you will see that there's not much change going on here, which is simulated here. Okay, so that is what this calculation means here. Okay, and now after that we have to calculate so now that we know the differentiated value of the function here, which is 0.4, it is this rate of change here times the weight. You can see that here. So we have the 3 here. So 1.1374 is this one, times 0.4, which is the weight. So this times this, okay, times the value here, 0.24, gives us a value of minus 0.013. Okay, so this is from this one, it influences minus 0.13. Okay, so this one. But we have one more here. We need this one. So 0.039, which is here, 0.039 times 0.45, which is this one, times same again, 0.24, which now gives us the sum of 0.009. So the rate of change is now calculated to be minus 0.009. So it's this one times that plus this one times that, okay, and of course time the differentiated. Huh? So this value here is almost 0.25 times this plus this times this one and this one. Hoo-ha. So that gives us this value. So that was the calculate local gradients. Now we know the influence of this node.